Good afternoon, young people. I'm going to try to make this as brief as I possibly can. Hopefully we'll get through this in less than 15. Today we're going to be talking about the thermochemistry of phase change diagrams. Now the reason we're talking about phase change diagrams is because we have some spots on that diagram that have some issues. The spots that don't have issues you're going to see are exactly the same as what we were talking about today. So it's called the thermochemistry of phase change diagrams, making sense of the plateau, because that's where we have the biggest issues. So let's look at phase change diagrams. We talked about this first year. We actually did an activity on it as well. Okay? Sorry, I'm adjusting a bit. So when we look at constructing a phase change diagram, we know what's happening is we start with a solid and we end with a liquid. So the first thing that we have to understand is in a phase change diagram, we have a couple of things. So let's look at some of the aspects of a phase change diagram. What we have here is we have our two axes labeled. We have this axis and this axis right here labeled. Notice that this is temperature and this is time. Time meaning the amount of energy I'm adding as time is going on. It's really a measurement of energy in terms of time. How much energy am I adding, okay? Then we notice once we get to the temperature part, we add some points. In this case, we have 0 and 100, and 0, 100 represent some specific points for water, and we're going to be specifically talking about water because it's a substance that we have a lot of. Sorry about that. I'm having a lot of stuff going on. So, we need to look at this from the perspective, right now we're talking about water. We know what 0 and 100 are for water. We know 0 degrees Celsius is the freezing point of water, melting point, and 100 degrees Celsius is the condensation or evaporation point or boiling point of water. So those are two important things, and you're going to see that in every phase change diagram. You will see these 2 points. There's always going to be the point at which there is freezing / melting, and there's a point at which there is boiling / condensing. Always will happen in every phase change diagram. Water is just a really common substance that we use a lot. So we're going to add heat, and when we add heat to a solid, what we notice happens is we can see that the temperature is increasing. As long as we have solid there, the temperature is going to continue to increase as long as it's all solid until we reach when? Until we reach 0 degrees Celsius. So at this point, we have a temperature change. So that means what's going on here? Heat's causing the temperature to increase in the solid. So the solid is getting warmer. So that's one phase. When we have only one phase, we can calculate the amount of heat added in the regular way. Delta H, or the enthalpy, is Q which is equal to M times C times delta T. Remember, delta H would be molar. We divide that by the number of moles, so that's a little bit funny there. But we have to remember we have a solid. So because we have a solid, the C for ice is different. Here's the C for ice. It's a little different than what we've looked at before because we've always had liquid water. So as long as there's a temperature change, I can use Q because I have temperature change. I need the specific heat. Once I know that, I can look that stuff up and I'll be good. So what's the next part of the phase change diagram? Well, the next part, what will happen next? Well, we will add more heat, but this time we're not just solid form. We actually have phase change happening. And when phase change is happening, we have melting going on. But at that point, there's actually an equilibrium between melting and freezing, melting and freezing, melting and freezing. But we're adding more energy. So the melting will eventually win out over the freezing. But until there is no more solid floating in the liquid, it will be at that point. It will be at the melting freezing point, the point at which that happens. So this is the problem. There are always two phases. The heat is going into loosening up the attraction. Temperature will not increase. That's our problem right there. We have no increase in temperature, excuse me. So no increase in temperature means that we have no way of using Q. So we have to figure out a different way to calculate, okay? And it's not as hard as you might think because we know something. If we know the information about the mass of water or the mass of the substance, we know how many moles of the substance. So what we are going to do is we are going to look at it from a different point of view. We are going to look at it from this idea of the heat, the molar heat of fusion of the substance. So the heat of fusion means What's happening there? Well, it's either fusing or it's melting, and the heat of fusion describes the point at which it's fusing together and becoming a solid, or the point at which it's going into a liquid. It's melting into a liquid, and it's the same thing. So we will use the mass. So let's say if we had 60.0 grams of water, we'd take that and divide by 18 grams. I'm going to get there. It's over 1 mole. And I'd get the number of moles of water that I had. And I would take that number of moles of water and I would multiply it by the heat of fusion, because now I'm going to be able to calculate the Q at that point. I don't need a temperature change. All I need to know is the amount of water, the grams of water that I have, and I need to know the heat of fusion, which we have right here, 6.02 kilojoules per mole. So it's pretty simple. When we're at the plateau, we basically have to use a little stoichiometry to find the number of moles of our substance, multiply that by the heat of fusion, the molar heat of fusion, and then we get the number of joules or kilojoules that we're going to have to use to get that much substance to go to a liquid. It's pretty simple. Okay, so then we go to the next phase. Next phase, what will happen next? Well, it's now only a single phase. It's all in liquid phase. So now temperature will rise once again. So now we have temperature rising once again. Now we can revert back to the same characteristics as the first time when we had a single phase. But this time when we're calculating heat, water is in the liquid phase. So what we have to remember is that the C for water in liquid phase is right here. It's 4.1, I add the 4 joules per gram degree Celsius, but you get the idea that for a different phase of substance, the C, the specific heat, is a little different because of what's happening there, the amount of energy it will take to draw in to do what it needs to do. Okay? So pretty simple. When you have a single phase, you can always go back to Q. Always go back to Q. Okay? So this is where evaporation will begin to occur. So at this point, you're going to have some molecules that are going to escape into vapor, but very few. So once we've reached this point and we've gotten up to a temperature of 100 degrees, what happens? Well, we plateau again, because now we have a point where we're boiling. We have both liquid and gas occurring at the same time. And because we have both liquid and gas occurring at the same time, we are at the boiling point. But you will notice, we aren't increasing temperature again. So that means we can't use Q. We can't go back and use that, but we can do the same thing that we did the last time, which is to use heat stoichiometry. In other words, I know the mass of the substance I'm using. I can figure out the number of moles, and if I know the heat of vaporization this time, I can figure out how much heat is added or needed to take that all from a liquid phase to a gaseous phase. So to make sure that happens. So I will add that into everything. So as we're going along, we have a couple of places that we're looking at, and I will show you that in just a second, okay? So what we're having is we have a part right here, A, that we have to have, B we have to have, C we have to have, D we have to have, and they're going to be additive. We're going to be adding all of those sections up together. So they have to be calculated separately and added together to get the total heat to take all of this stuff, or how much ever water to whatever point. Okay, so at this point, what will happen next? Well, after we've at 100 degrees and everything has gone from a liquid into a gas, we have a temperature change again. Okay, we have a temperature change again. So again, it's a temperature change, same characteristics as before. We have a single phase, therefore we can go back to Q. And we have to understand that water in vapor form has a C of this. Now I have to make sure, because those are looking a little strange, because the one for solid and the one for liquid are very close to the same. I'm thinking this one is smaller, but I'll get back with you on that in just a second. Let me look it up, as a matter of fact, really quickly. Okay, hang on, I'm Googling really quickly. All right, it's taking me longer than I would like it. sorry. It's taking me longer than I would like here. I'm just trying to make sure I have the right number. Okay, ice. No, it's about the right number. Okay. Hang on. Kilojoules. No, that would be right because if I'm in kilojoules to, yeah, okay. So what I looked up, it says it's 1.996 joules per gram degree Celsius. Okay. So, you know, it's closer than I thought it was. All right. Sorry about that. Didn't mean to confuse the situation. So once again, we take the mass, we'd find the number, we'd find heat just the regular way like we always have. Okay. So why is steam so dangerous? Well, because, you know, we have a very, very small amount of C, so, and it's, you know, in gaseous phase, and it can hurt us pretty bad. So it's pretty bad. Change the location of the plateau. How can we change the location of the plateau? Very simply, we can change the pressure. If we change the pressure, we change where water boils and water does other things. So it only boils at 1 atmosphere at 100 degrees Celsius. So if we change the pressure, we change the boiling point. That's what happens in Denver because we've changed the pressure. The boiling point is actually lower. Add something to the water. So if we add like salt to the water, we basically keep it in liquid phase longer. So like antifreeze or adding salt to water in the wintertime helps keep things from freezing up. How do we change the length of the plateau? Well, we can change the amount of substance. We can, so we can change the amount of substance, basically change the length of the plateau. The more substance we have, the longer the plateaus will be. How to change what the plateaus look like? Well, we can supercool it. When we supercool it, we cool it too quickly and it doesn't have time to organize, so the temperature drops even though it shouldn't. And so we see some little dip-de-dong. So we have this flat line and then we see this dip-de-dong and then it goes back up. And that's just a process of supercooling. We can also superheat something. If we heat it too quickly, what ends up happening is we heat really, really fast, and it continues to rise even though you're not adding the heat as fast, and then it will come back down and plateau again eventually. So there's some processes here. So if we were looking going backwards, the graph looks very similar going backwards. You're going to have the exact same points. But remember, condensation and freezing are the opposite of melting and boiling, but the heat, the delta H of fusion and the delta H of vaporization are still appropriate for those two spots because they're basically opposites, and so they'll have the same basic number magnitude, but they'll be in opposite directions. So don't worry about it too much. So hopefully this gets you through those 4 little problems on that worksheet. All right, thank you very much.